This is an example of how to solve a problem dealing with gaseous reactants from Chapter 5 of our textbook. So the problem deals with the isolation of lead that begins by roasting lead-2 sulfide, also known as galena, a process that occurs in many states in the US. The main product of this process is the production of lead-2 oxide, which eventually will be turned into lead, and the production of a pollutant called sulfur dioxide. So this problem deals with the question, how many liters of sulfur dioxide measured at STP are produced by the reaction of 3.75 kilograms of galena with 228 liters of oxygen gas at 220 degrees Celsius and 2 atmospheres of pressure. And part B is, what is the total volume measured at STP after the reaction is completed? So think about this problem, propose a plan to solve the problem, and start solving the problem. You may pause this video while you are solving the problem before you look at the answers. So in order to solve this problem, for part A, we will need to write the balanced equation. There are two reactants, lead-2 sulfide and oxygen. So this implies that this is going to be a case of a limiting reactant. The second step would be to use the molar ratios of the chemical reaction to calculate the moles of sulfur dioxide produced by the limiting reactants. And finally, we will use the ideal gas law to determine the volume of sulfur dioxide that has been produced. In part B, this is a conditional part. If the limiting reactant is not oxygen, this gas will not contribute to the total volume. And if oxygen does contribute, then we add the remaining moles of oxygen and the moles of sulfur dioxide produced in step 2 of part A before using the ideal gas law to calculate the volume. The reaction that is behind this process consists of the reaction of lead sulfide, which is a solid, or galena, oxygen gas, to form lead oxide, which is a solid, plus 2 moles of sulfur dioxide, which is a gas. Need to continue balancing this equation. 2, 3, let's double check, and 2. So we have 2 leads, 6 oxygens, 2 and 4 oxygens, that's 4, and 2 sulfides, 2 sulfurs, 2 sulfurs. Okay, so now we're going to calculate the number of sulfur dioxide produced from oxygen. So what we will be doing is writing all the information that we have regarding the oxygen that is used for the reaction. So for oxygen, we know that we have a volume of 228 liters. The pressure is 2 atmospheres. The temperature is going to be 220 degrees Celsius. And we need to solve for N. That is based on PV equals nRT, the ideal gas law. So we will need to be solving for N, which is going to be equal to PV over RT. Before we solve for N, we need to make sure that we have the correct dimensions. Pressure is in atmospheres, volume is in liters, the temperature needs to be in Kelvin, so we are going to continue by saying that the temperature is 220 plus 273, which equals to 493 Kelvin. Okay, so we have the correct temperature. And R, the value of R is going to be that uses liters, atmospheres, and Kelvin. So replacing these values into this expression, we get that atmospheres, liters, liters, atmospheres, mole, Kelvin. And the last term of this is the temperature, which is 493 Kelvin. We can cross out units, atmospheres, atmospheres, liters, liters, Kelvin, Kelvin. And if we do the mathematical calculation, we solve for n, and we get a total of 11.2627 moles of O2 gas. From 11.2627 moles of oxygen, we can calculate the number of moles of SO2 that will be formed. So we're going to use the reaction stoichiometry, multiply this by 2 moles of SO2. I will not add that is a gas, corresponding or coming from 3 moles of O2, as we can see from the reaction. And that is going to give a total of 7.5085 moles of SO2 gas. So now we need to find out what would be the number of moles of SO2 if we consider lead sulfide as the reactant. So that is going to be equal to, so moles of SO2, again we are taking this as the reactant. We have 3.75 kilograms of lead sulfide. We're going to change kilograms to grams. So the factor is 1,000 grams per kilogram. We're going to use the stoichiometry of the reaction. We have 1 mole of lead sulfide per, I need to correct that a little bit. We're going to take the molecular weight of lead sulfide, 1 mole of lead sulfide corresponds to 239.3 grams of lead sulfide. And finally, we are going to multiply by the stoichiometry of the reaction, which basically is 2 moles of sulfur dioxide per 2 moles of lead sulfide. I would not put it here because we are running out of space. So the net result of this calculation is going to be, we're going to cross out some units beforehand, kilograms, kilograms, grams, grams, and then this corresponds to these moles here. So the net result will be 7. That's not correct. Let me correct that. 15.6707 moles of sulfur dioxide. Okay, so now what we need to do is to compare the moles of sulfur dioxide that would be produced if we use oxygen, all the oxygen, which is basically 7.5, versus the moles of sulfur dioxide if we use galena or lead sulfide as the limiting reagent, which is 15.675. The smallest of these two is this number, So oxygen is the limiting reagent. We said that oxygen is the limiting reagent or reactant. And the number of moles that we have produced of sulfur dioxide based on oxygen are 7.5085 moles of sulfur dioxide. So we will use the ideal gas law and solve for volume. And replace the different information that we have available for this particular problem. We are asking for the information to be given in SDP, standard temperature pressure. Temperature, SDP, is 273 Kelvin. Pressure is 1 atmosphere. So we're going to replace the values that we have now. And please note that I'm skipping some steps here. I'm not writing all the dimensions for the R constant, but I'm keeping track that the dimensions are correct. I have moles here, atmospheres of pressure. This will be Kelvin in temperature, and then I can use that type of constant. And if I solve for volume, the result is that is 1.7 times 10 to the second liters of SO2 gas. And this is the answer for part A. Part B is interesting because it asks what will be the total volume. But in this particular example, since we have that oxygen is the limiting reagent, O2 was consumed. That means that there is no oxygen left at the end of the reaction. Therefore, the final volume or total volume is the same as in part A, which is 1.7 times 10 to the 2 liters of total volume. And this is the end of this example.